Hey guys, this is my fourth video of STR, and in this video we'll be discussing the loss of simultaneity. Now, the motive behind this video is to help you understand the concept behind loss of simultaneity, not just the how to solve the questions in exams, but how does it happen and why it does. Now, loss of simultaneity states that two events that are simultaneous in one inertial frame may not be simultaneous in another inertial frame of reference. This is a little difficult to visualize because we don't deal with relativistic velocities in real life. Now, why does that happen? The difference in time measurement in different inertial frames raises the need to re-examine simultaneity of two different events in different inertial reference frames. This means that difference in perception of time leads to the fact that observers in different inertial frames no longer agree on the perception of time. Time for a moving object passes slower than for a stationary one. Now, let us take two frames of reference S and S dash, where S dash is moving with the velocity v with respect to S frame, and let two events A and B occur at the exact same time with respect to S frame. Now, the loss of simultaneity states that these two events A and B will not be simultaneous in S dash frame. Let us take two synchronized clocks 1 and 2. Now what I mean by synchronization is that when these two clocks are measured at the exact same time, they give the exact same measurement. Now let us take one of these clocks and put it in a rocket with a velocity v. Now as soon as the rocket starts moving, we'll start noticing a difference between the measurements of two times. Time passed according to clock 1 will be more than time passed according to clock 2. Now, if velocity was 0.5 c and time in clock 2 measured out to be 5 seconds, time in clock 1 would measure out to be 10 over root 3 seconds. Now, we'll soon come back to the mathematics of this concept, but first we need to realize the concept and the reasoning behind the loss of simultaneity. Now let us take a real life example in which a train having length 2L dash is passing through a platform at speed v, which is much less than c. In the middle of the train is a machine which ejects two balls 1 and 2 with same speed u, and here we will have minus u because we are considering velocity. At the two ends are detectors A and B, with A at the front and B in the back. For the passenger in the train, the balls will have equal speed and reach A and B simultaneously, obviously. For observer on the platform, however, the balls will have different speeds. That is, the ball traveling towards A will have velocity u plus v, and ball traveling towards B will have velocity minus u plus v. Now, let dt be the time the ball takes to reach A. Now, in time dt, the train has moved forward by v dt. So, this is v dt and this is also v dt. Now, according to the observer on the platform, the distance the ball travels to reach A, L of A equals L dash plus V dt. Therefore, U plus V dt equals L dash plus V dt. Therefore, U dt equals L dash. Now, we need to check that whether in time dt the ball has reached at the end B or not. So, for ball moving towards B, the distance traveled is minus of minus u plus v dt, which is equal to u minus v dt, which is equal to L dash minus v dt, which is exactly equal to this distance. Here this much. So, in time dt, the ball reaches A and B simultaneously. So, in realistic case, in the that is in the cases where velocity of objects is much smaller than speed of light, the ball reaches A and B at the exact same time. That is, the events that are simultaneous in one reference frame, that is our train, is also simultaneous in another reference frame, that is our platform. But now I will show you that this is not the case if the S dash frame has a relativistic velocity. Now let us take the same scenario, but in this case the speed of the train, that is v, is comparable to speed of light, and instead of balls we are throwing photons towards A and B. Inside the train, the light having the speed c has to travel a distance of L dash in both cases. So they reach the ends A and B at the same time. That much is pretty simple. But for the person standing on the platform, the length of the train changes to L, which is L dash root 1 minus v square by c square. As in this case of the ball, the photon has to travel less distance than this to reach B, but more distance than this to reach A, because the train has moved forward by the distance v dt. However, there's one main difference between the balls and the photons. While the velocity of the balls changed according to the reference frame to maintain simultaneity, here reverse happens. The order of events change here to make the speed of light same in all inertial reference frames, because if the photons behaved like balls, then photon 1 would have a different velocity than photon 2, and as we discussed before, light, no matter in which inertial reference frame, has the same velocity. So here, to maintain the velocity of light, the simultaneity has to pay a price. So in this case, the light reaches B before A. This is because A is moving away from the light, whereas B moves towards it. So the events which seem simultaneous in one inertial frame, that is our train, are not simultaneous in another inertial frame, that is our platform. Here is a way we can calculate the time it takes for light to reach frames A and B with respect to S frame. As you can see, T1 is not equal to T2, even though T1 dash is equal to T2 dash, mathematically proving that simultaneity is lost. I hope you understand why the simultaneity is lost at relativistic speeds in a conceptual manner. In the next video, we will discuss about the mass variance, relativistic momentum and energy. I might also make a video explaining one of the weird consequences of loss of simultaneity, that is the effect it has on our personal timelines. Thank you very much for watching the video, and please don't forget to like, share and subscribe.